Section 4.9, numerical integration. So remember that our definition of the definite integral is the following. So it's integral from a to b, f of x dx is the following limit when n goes to infinity, summation f at some point xi, delta x, I running from 1 to n. Also, we have fundamental theorem of calculus, which is the following, that if you have this definite integral, then you can calculate it using the antiderivative, and it will be antiderivative at point B minus antiderivative at point A. But the problem is that sometimes it's really hard or even impossible to calculate the antiderivative. And there is standard example that came from the probability theory, the following integral from minus infinity to some point, say t, exponential of minus x squared dx. And unfortunately, you cannot express this important integral in terms of some usual functions, trigonometric or polynomial, rational function, whatever. So it's impossible to find the antiderivative. So this integral has no antiderivative. But if you are still interested in, say, the following integral from minus infinity, say, to minus 1, exponential of minus x squared dx, what you should do? Because still in probability it appears, and you want to know what is the value. And there are several ways. First of all, you can approximate this integral using our Riemann sum, right? Because by definition it is this limit when n goes to infinity, summation, I runs from 1 to n, f of xi, delta x, and so on. But instead of considering limit, you can say that it's approximately this summation, f of xi, delta x, and very large number, then it will give you a nice approximation. Of course, it will not be exactly this integral, but it will be a nice approximation. And this kind of first way how you can numerically integrate is just using the Riemann sum. But it turns out that there are other options that are slightly more intelligent than straightforward Riemann sum. And first of them is called trapezoidal rule. So recall that when we define our integral, we approximate the area under the curve by some rectangles and then sum up the areas of such rectangles. So we divided our interval from a to b into n subintervals, and on each subinterval we considered the corresponding rectangle. And then we sum up all such areas and consider the limit when n goes to infinity. And in trapezoidal rule, instead of that, you also divide your interval AB into subintervals, but now you approximate it not by rectangles, but by trapezoids. So this is one, this one another, and you connect them in this way. And then you connect in that way. And in this way. So these are trapezoids, while initially we had rectangles. And you repeat the same steps. You consider the area of all these trapezoids, then sum them up, and that will give you an approximation of your area. So let's recall what is the area of a trapezoid. So I'm interested in a very special case when my trapezoid has right angle at the bottom and some angle on the top. So suppose that this side has length A, this side has length B, and base has length H. Then the area is equal to 1/2 sum of the sides times the base. Let's apply this in our case. We have our initial point A that we'll call x0, our final point B, which will be xn, and we divide this interval into n subintervals of equal length. So this is my x1, this is my x2, and so on. Then, as we discussed, we consider the corresponding trapezoids. And let's calculate the area of the kth trapezoid. So I have here xk, and this is my xk plus 1. And let's calculate this area. As we discussed, area of this trapezoid is 1/2 times sum of the sides. So one side is just the value of my function at point xk, while the other side also is value but at different point, which is xk plus 1. And so it's f of xk plus f of xk plus 1 times the base, but the base is just the length of our subinterval, so it is delta x. Remember that we divided AB into n subintervals, each of them has length delta x. So this is delta x also. And the last step is to sum up. So this is area of kth trapezoid, and thus area under the curve, which is integral from a to b, f of x dx, is approximately sum of these areas of trapezoids. So I started with my first trapezoid, and it gives me 1/2 f of x0 plus f of x1. This is my times delta x. This is my first trapezoid. Then I have my second trapezoid, which is 1/2 f of x1 plus f of x2 times delta x plus so on. And the last one will be 1/2 f of x n minus 1 plus f of x n times delta x. And I see that I can combine some terms. So for example, I have f of x1 delta x, and I have the same in the second term, is coefficient 1/2. And x0 is my a, while xn is my b. So we see that every point appears twice except x0, which is a, and xn. And so, yes, first of all, I observe that delta x is common factor, so I can write it in front, and then I have 1/2 f of a. Then I have f of x1 delta x times 1/2 plus the same from the second term, so I get just f of x1. Then I have the same story with x2, x3, and so on until f of xn minus 1. And the last, which is f of xn, which is the same as f of b, but it appears only once, so it has coefficient 1/2. And that's what is called trapezoidal rule. So we can approximate our integral from a to b, f of x dx, not by the Riemann sum, but by this sum, 1/2 f of a plus f of x1 plus f of x2 plus so on, plus f of xn minus 1 plus 1/2 f of p. So this is trapezoidal rule, which is just approximation of the initial integral using not rectangles but trapezoids. And let's do simple example. Use the trapezoidal rule when n equals 4 to find the approximate value of the following integral. From 0 to 1, x squared dx. So what should we do? N equals 4, trapezoidal rule. So first of all, we need to calculate our delta x, so which is length of our subintervals. So in general, it is b minus a divided by n, but in our case, it is 1 minus 0 divided by 4. So it's 1 over 4. Then first point x0 is equal to 0. Second one, which is x1, will be x0 plus delta x, so it will be 1 over 4. x2, by the same reason, is x1 plus delta x, and it will be 1 over 4 plus 1 over 4, which is 1 over 2. X third will be x2 plus delta x, and it will be 1/2 plus 1 over 4, and it will be 3 over 4. And the last one, as we expected, x3 plus delta x will be 4 over 4 or 1. So our point B. And then we just need to evaluate our function at those points and then use the trapezoidal rule. So our function f of x is x squared, thus f of a or f of x naught is equal to 0, f of x1, which is f of 1 over 4, is 1 over 16, f of x2, which is the same as f of 1/2, is 1 over 4, and f of x3, which is f of 3/4, will be 9 over 16, and the last point, which is the same as f of b, which is the same as f of 1, will be just 1. And so our integral from 0 to 1 x squared dx thus can be approximated using trapezoidal rule by the following expression. So delta x times 1/2 f at point x0 plus f of x1 plus f of x2 plus f of x3 plus 1 over f of x4. And we just calculated all expressions that we needed. So delta x is 1 over 4, which is 1 over 4 times 1/2 f of x0, which is the same f of a, times 0 thus, plus f of x1, which is 1 over 16, plus f of x2, 1 over 4, f of x3, 19 over 16, and 1/2 of the last one, which is just 1. And you can combine it and get that it's approximately 0.344. Of course, we can, in this case, we indeed can integrate, because in this case, the antiderivative is simple one, and it's x cubed over 3, substitution from 0 to 1, and it will be 1 over 3, which is 0.333, and so on. So even for n equals 4, our approximation is not that bad. But of course, if you consider it n equals 400, then your approximation will be much better. But for us, it's enough. Another rule of numerical integration, which is called Simpson's rule. So idea is the following. You still have some function, and say you're interested in integral from a to b. This is your integral that you're interested in. First of all, you divide your interval ab. So divide into n equal subintervals of equal length. So far nothing new, but here we have one restriction that n should be even, and this is important. So you divide it, something like that, and then consider 3 points. A will be your x0, then you have x1 and x2 and so on. And let's calculate the value of our function at those points. So I have this point, and this point. And so before we had, in case of Riemann sum, we needed to choose only one point somewhere in the interval. For the trapezoidal rule, we used 2 points, 2 endpoints of the interval, while here I need 3 points. And I will construct the parabola that goes through these 3 points. So it will look like that. So this is my parabola that goes through these 3 points. So instead of rectangles or trapezoids, I'm using, in this case, parabola. And I will approximate my area under the curve as an area under this parabola. So indeed, even on my picture, it looks like very good approximation. And you can show that if you have a parabola that goes through 3 points, first of all, to determine the parabola, so general equation for the parabola looks like this: ax squared plus bx plus c. So you have 3 parameters, thus you should have 3 points. That's what happens here. So this is your x2, and this is your x3. So 3 points determines your parabola. Okay, let's call them x0. So this is our first parabola, x0, x1, and x2. And the corresponding y values will be y0, y1, and y2. And remember that we have our subintervals of equal length, delta x. So this is my delta x. And then you can show that the corresponding area under this parabola will be delta x over 3, y0 plus 4y1 plus y2, where delta x, as we discussed, if we have interval ab and n subintervals, then delta x will be b minus a divided by n. And so we can calculate this area under the parabola passing these 3 points. And that will be our approximation of our curve on the interval from a to x. And then you continue doing that. So next you consider interval from x2 to x4. And so you have this point, this point, and this point. And again, you approximate your curve using another parabola that goes through these 3 points, probably like that. And again, you can calculate area under the green parabola, but using now y2, y3, and y4. And you keep going. And so what you will get? our integral from a to b f of x dx, which is the same as area under the curve f of x from a to b, thus can be approximated by the areas of these parabolas. So first parabola gives you delta x over 3 times, that's what we just discussed, y0 plus 4y1 plus y2. Second one, so now you started with y2, then you have 4y3, and the last one is y4. And third parabola that on the interval y4, y6 gives you this y4 plus 4y5 plus y6, and so on. And the last one will be delta x over 3 yn minus 2 plus 4yn minus 1 plus yn. This will be the last parabola. And you see that y2 appears twice. It appears here and here. And also you can see that delta x over 3 is common because our subintervals have the same length, so it's not a surprise. And finally, you can simplify it and see that this is the same as delta x over 3, which is common factor, times y0 plus 4y1 plus 2y2 plus 4y3 plus 2y4 plus 4y5 plus 2y6 and so on. And the last three will be 2yn minus 2 plus 4yn minus 1 plus yn. And this approximation procedure is called Simpson rule. So what we get? We get that integral from a to b f of x dx can be approximated by the following sum. So it's delta x over 3 f of x naught, this is just y naught, plus 4 f of x1 plus 2 f of x2 plus 4 f of x3 and so on. And the last three will be 2 f of xn minus 1 plus 4 f of xn minus 1 and f of xn. Okay, so, and yes, where delta x is b minus a divided by n, and n is even. Why n should be even? Because otherwise you will not have enough points to construct the last parabola. If it's odd, you will get only 2 points or 1. We can see that now the rule is slightly more complicated because we have many different coefficients. First of all, we have delta x over 3. We have 1 in front of the first point. Oh, sorry, this should be f of x. And 1 is coefficient for the last one. While in the middle, you have alternating coefficients. So it's 4, 2, 4, 2, 4, 2, and so on. Let me make a remark. For the Riemann sum, we have just delta x, and the coefficients are just 1, 1, and so on. For the trapezoidal rule, we have also delta x, and the coefficients are 1/2 for the, so first one has coefficient 1/2, then you have all ones except the last one. And for the Simpson's rule, you have delta x over 3, and the coefficients are 1, and then they alternate 4, 2, 4, 2, and so on. Then you have 2, 4, and the last one will be 1 again. So that's the sequence of the coefficients. And also, for the Simpson rule, n should be even. For the first two, n can be even and odd, while for the Simpson rule, it has to be even. And let's do one example. So let's approximate the following integral from 0 to 1, x squared dx. Say n is equal to 4. Our delta x is 1 minus 0 divided by 4, so it's 1 over 4. And thus, my x0 is 0, my x1 is 1 over 4, x2 is 2 over 4 or 1/2, x3 is, so each time I'm adding delta x to obtain new x. x3 will be 3 over 4, and the last one will be, of course, 1. And thus, f0, which is f of x0, will be, our function is x squared, so it will be 0. f1 will be 1 over 4 squared. f2 will be 1 over 2 squared. f3 will be 1 over 4 squared. And the last one will be just 1. So it's 3 over 4. And so I can use the Simpson rule and get that this integral dx will be approximately, so first of all, I have delta x divided by 3. So I have 1 over 4 and also divided by 3. Then I have my coefficients should be 1, f0, so 1 times 0. Then I have alternating 4, 2, 4, 2, and so on. So it's 4 f1, which is 1 over 4 squared, plus 2 f2, which is 1/2 squared, plus again 4 times f3, which is 3 over 4 squared, and plus, since it's the last one, the coefficient is 1, f of 4, which is just 1. And you can calculate and get that it is 0.333. So when we used trapezoidal rule, we got for the same example, x squared, we got that the area was approximately 0.344, while the exact value is 0.33. So we see that Simpson's rule gives us much better approximation. And the very last remark, numerical integration, it is useful when you cannot calculate the antiderivative, that's what we discussed, but also it's useful when you have sets of experimental data, when you don't have actual function, but you only knows its values at some specific points. Because indeed, what you need to know, if you look, say, at Simpson's rule, you only need to know your delta x, the interval that you measure, and you just need the value of your function at those specific points. And then you can find the corresponding area or corresponding integral.